morning students. Today let's look at the next aspect of complex variables. We'll go into the power series of functions. Essentially there are two types of expansions. One is known as the Taylor's expansion and the other is known as the Lorentz expansion. Particularly when you come to Lorentz expansion, it has got a very important role to play in the evaluation of contour integrals. But first let us look at the Taylor series. Suppose we have a function f of z, a complex function, and you need to expand it around a point z0. This is known as the center of expansion. The power series of this function, which is also called the Taylor's expansion, is given by f of z0 plus z minus z0 into f dash z0 plus z minus z0 whole square by 2 factorial f double dash z0 and so on, which you can compactly write as summation n is equal to 0 to infinity fn z0 by into z minus z0 to the power of n by n factorial. For n is equal to 0, you get this term. For n is equal to 1, you get this, and so on and so forth. So as I told you, z0 is called the center of expansion, and you will observe that in this expansion there are no negative powers of z minus z0. This is only possible when the function f of z is analytic. In fact, every analytic function will have a power series about a designated point z0. Conversely, every power series corresponds to an analytic function. But when you come to the Lorentz series, you can have expansions about singularities, about which we'll discuss immediately. But let us look at a very small example of a Taylor's expansion. Suppose we have f of z is equal to 1 by z minus 3, and we want to expand in powers of z. When I say powers of z, I mean powers of z minus 0. In fact, when you put z0 is equal to 0, the Taylor series is called the Maclaurin series, and Maclaurin series will contain powers of z. Therefore, in this question we are looking for the Maclaurin series of the function. So you can write this as z minus 3 whole inverse, and you can say, if you take in fact you can write this as minus of 3 minus z whole inverse, from which you can take 3 out, you will have that. You must be careful not to take z outside, because that will lead to 3 by z situation, and that will create a singularity at z is equal to 0. Because we want in powers of z, we are looking for the Taylor's or Maclaurin's expansion. So this will be minus 3 into 1 plus z by 3 plus z by 3 whole squared and so on. So you can also summarize this as minus 3 summation n is equal to 0 to infinity z by 3 to the power of n. So this will be the Maclaurin's expansion of this function about z is equal to 0. Of course, if the question is in powers of some z minus a or z plus a and so on, you must manipulate this function to contain those powers. But you must be very careful to see that we are giving a series expansion in such a way that we don't have negative powers of z. Then it is called a power series. So we'll have to be very cautious about what is the nature of the expansion. Positive powers of z and also negative powers of z will take you to Lorentz. If it's only positive powers of z or z minus a or z plus a, then we are with Taylor's. So let's first look at a few problems on Taylor's, then we'll go to the Lorentz series and see how we can expand in different regions and how we can discuss the concept of singularities and the nature of singularities and how that will lead to the calculation of residues and subsequently evaluation of complex integrals. Okay friends, before we embark on some questions on Taylor series, we must basically remember that certain series are very valuable when you start solving problems. Suppose we have e power mz, then you can remember the expansion is 1 plus mz plus mz whole square by 2 factorial and so on, which can be compactly written as summation n is equal to 0 to infinity mz to the power of n by n factorial. So m can take any real value or even complex. Then sin z, z minus z cube by 3 factorial plus z power 5 by 5 factorial and so on. So which can be compactly written as summation n is equal to 0 to infinity, because only odd powers of z are coming, z to the power of 2n plus 1 by 2n plus 1 factorial with a minus 1 to the power of n to indicate that it's an alternating series. When it comes to cos z, 1 minus z square by 2 factorial plus z power 4 by 4 factorial minus and so on, which can be compactly written as summation n is equal to 0 to infinity. Again we have the alternating sign pattern, so include minus 1 to the power of n, z to the power of 2n by 2n factorial. Natural log of 1 plus z is z minus z square by 2 plus z cube by 3 minus and so on, which can be compactly written as summation n is equal to 0 to infinity, again minus 1 to the power of n, z to the power of n plus 1, with n is equal to 0 you get z there by n plus 1. So like this we can remember a few important expansions which can be very useful. With the log of 1 minus z, replace z with minus z and you will get a corresponding expansion. And we may also remember that sin I theta is I sin h theta, cos I theta is cos h theta, which are also valuable pieces of information while you are solving problems on expansions. Many more are there, but as we do problems, let us discuss all of them. I think to this list we must definitely add 1 by 1 minus z, which is summation n is equal to 0 to infinity z to the power of n. This is a geometric series. Actually, when you expand it, you will get 1 plus z square and so on. This is called a geometric series. 1 by 1 plus z is similar, but you will have to put a minus 1 to the power of n for that. So these are also very useful Maclaurin expansions. And of course, we can also discuss 1 minus z whole square and so on and so forth. If you are familiar with intermediate binomial theorem, all those things can be used. So let's now begin a small exercise how to tackle problems on Taylor series. Just before we start, once again, a Taylor series always produces positive powers of z minus a, and when a is equal to 0, the same series is called a Maclaurin series. Question number 1. What is the Taylor's expansion of f of z is equal to cos hyperbolic z about z naught is equal to pi I? Now this is the center of expansion, so we must go for a Taylor's. So the general formula will be f of z is equal to f of z naught plus z minus z naught into f dash z naught plus z minus z naught whole square by 2 factorial f double dash z naught and so on. Okay. So, we will have to take derivatives of cos hyperbolic z at the point z naught. So, let us begin with f of z is equal to cos hz, f of pi I, z naught is pi I in this case, is cos hyperbolic pi I, which is cos pi, which is minus 1. F dash z is equal to sin hyperbolic z, mind you there is no minus sign, f dash pi I is sin hyperbolic pi I, which is I sin pi, and sin pi is 0. Now you can see that you get alternate zeros. Let us look at f double dash z, which is again cos hyperbolic z. So, which is a repeat of that. Therefore, f double dash pi I will be again minus 1. Again f triple dash pi I will be exactly the same as the fifth derivative at pi I, all of them will be 0 and so on. And fourth derivative will come from here. Fourth derivative will be again a repeat cos hyperbolic z. So, the fourth derivative at pi I will be again minus 1. So, you can see that this first term, third term, fifth term and seventh term are all the non-zero terms. The even terms, wherever sin hyperbolic z appears, will all produce zeros at the point pi I. Therefore, if you substitute in this series, cos hyperbolic z is equal to f of z naught is minus 1, then this is a 0 plus z minus pi I whole square by 2 factorial into minus 1, then the next term is 0 plus z minus pi I to the power of 4 by 4 factorial into minus 1 and so on. Since all the terms are negative, we can extract a minus sign, then inside the bracket all are positive. So, summation n is equal to 0 to infinity and the powers are all even, and the first term can be visualized as z minus pi I to the power of 0 by 0 factorial. So, z minus pi I to the power of 2n by 2n factorial. So, this should be the expansion of hyperbolic z around pi I. This is a compact way of writing. One must get used to this notation because answers generally may not be printed like that. So, the correct option for this problem is D. Question number 2. What is the coefficient of z to the power of I in the Maclaurin expansion of f of z is equal to e power z sin z about z is equal to 0? Well, there are two ways of doing this. You can treat this as a single function and go and keep on differentiating 5 times and you determine the coefficient of z to the power of 5. But you can also see that e power z and sin z have standard Maclaurin expansions. I am using the word Maclaurin expansions because we are looking for z to the power of 5. That means the center of expansion is 0. So, we can write this as one plus z square by 2 factorial plus z cube by 3 factorial plus z power 4 by 4 factorial plus z power 5 by 5 factorial and so on. I have written till this point because we need the coefficient of z to the power of 5. And coming to sin z, the standard Maclaurin expansion is z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial and so on. Since we need the coefficient of z to the power of 5, let us look at the possibilities. This one can be combined with z to the power of 5 by 5 factorial, and you will get a coefficient of z to the power of 5 is 1 by 5 factorial. Then this z cannot be combined with anything to produce z to the power of 5 because all the powers there are odd. But this z squared can interact with z cube to give you a coefficient, but that will be a negative term. It will be minus 1 by 2 factorial into 3 factorial. Then this z cube cannot interact to produce z to the power of 5, but this z to the power of 4 can interact with this. That will be a positive term, and that will be 1 by 4 factorial. And this z power 5, even though we have written, does not interact. In fact, it produces higher powers. So these are the three possibilities. We close. Let's simplify this. This is 1 by 120 minus 1 by 2 into 6, 12 plus 1 by 24. 120 is the LCM. You get 1 minus 10, 24 5s are. So you will get minus 4 by 120, which is minus 1 by 30. So this happens to be the coefficient of the z to the power of 5 in the expansion. And we have clearly avoided any differentiation. We have used the knowledge of e power z and sin z Maclaurin expansions. So you can find option C shows minus 1 by 30 is the correct answer. Question number 3. What is the expansion of f of z is equal to tan inverse z about z is equal to 0? So once again, it's a Maclaurin series application. There are at least 3 possible ways to solve this example. One is to actually take the derivatives of tan inverse z. Of course, after 2 derivatives, the labor increases. We can look at one nice method. That method is, you first consider 1 by 1 plus z squared. You know this is related to tan inverse z as a derivative of tan inverse z. So this can be written as 1 plus z squared whole inverse, and this can be given by normal expansion, and we will have 1 minus z squared plus z to the power of 4 minus z to the power of 6 and so on. If you now integrate the left hand side produces tan inverse z, whose expansion we are seeking, and this is term by term integration z minus z cube by 3 plus z power 5 by 5 minus z power 7 by 7 and so on. Perhaps this is the fastest way by which we can produce the power series expansion of tan inverse z. As I told you, the other option is you can actually seek derivatives and build a Maclaurin series. There is a third method which is generally not taught for competitive exams. That is, you take the derivatives through the Leibniz theorem for successive derivatives, but we don't recommend that for this type of exams. So the correct option for this problem is A. Question number 4. What is the expansion of f of z is equal to 1 by z minus 1 into z minus 2 about z naught is equal to 0? So, as all of you can guess, we first have to get the partial fractions for this. So, you let 1 by z minus 1 into z minus 2 is equal to a by z minus 1 plus b by z minus 2. So, a will be 1 by 1 minus 2 and b will be 1 by 2 minus 1. So the partial fractions are 1 by z minus 2 minus 1 by z minus 1. So these are the partial fractions. So write your f of z like that. Since we are looking for the power series, we will have to write this in the reverse direction 2 minus z, for which you have to take a minus sign common. So minus of 1 by 1 minus z minus 1 by z minus 1. In fact, this will be plus z minus 1. You have to reverse the sign here. This is 2 minus z. So 1 by 2 minus z minus 1 by 1 minus z. So now you can give expansions, but here we must take 2 outside. So write it like this: 2 into 1 minus z by 2 minus of minus plus 1 by 1 minus z. So this is minus half 1 minus z by 2 whole inverse plus, now both of them can be easily expanded. So minus half into 1 plus z by 2 plus z squared by 4 and so on, plus 1 plus z plus z squared and so on. If you find that the number of terms in the expansion is not sufficient, you can add 1 or 2 more terms. But let us see what happens. Let's first correct the coefficients. 1 minus half plus minus 1 by 4 plus 1, 3 by 4 z plus minus 1 by 8 plus 1 is 7 by 8 z squared and so on. So this is the Maclaurin's expansion or power series expansion of this function about z naught is equal to 0. So you can find that the correct option is option A. So these type of examples, even though are simple, is better to practice because we will be in touch with the binomial expansions. And of course this I have used the same type of power series, 1 minus z naught to the power of minus 1, that has been highlighted in this example. But you can always have examples with higher powers, for which if you remember the binomial expansions, they will all look very, very similar. Let's go to the next question. Question number 5. What is the power series expansion of f of z is equal to log of 1 plus z by 1 minus z in the region mod z less than 1? In fact, one must understand that this is called the region of convergence. It is within this region that the expansion of this function is valid. So the easiest way to solve this problem is to use the property of logarithms and use their respective expansions. Please observe one thing: mod z less than 1 means mod z minus 0 less than 1. That means the center of expansion is 0. So it is enough to write the Maclaurin series for both these functions. So this, as we have seen earlier, is z minus z square by 2 plus z cube by 3 minus z power 4 by 4 and so on. And this is minus of z plus z square by 2 plus z cube by 3 plus z power 4 by 4 and so on. So this becomes minus of minus plus. The moment it is plus, the minus z square by 2 and plus z square by 2 minus z power 4 by 4 plus z power 4 by 4 will vanish, and the rest of the terms will become double. So 2 times z plus z cube by 3 z power 5 by 5 and so on. This can be written as twice summation n is equal to 0 to infinity. The powers of z are all odd, so let us write z to the power of 2n plus 1 by 2n plus 1. So can sample test, put n is equal to 0, you will get z to the power of 1 by 1, that represents this one, n is equal to 1 will produce this term and so on. So you will find that option D is available, showing this is the correct answer.